Uh, Hello everyone. Welcome to the live problem solving session for week 11 of the course Computational Competitive Algebra. So this course is instructed by Professor Manoj Kummini, and this is the second last week of this course. So let's quickly review the topics which we were studying in week 11. Okay. In week 11, again we started with the graded ring, basically n graded rings, and we defined the proj of a graded ring. So proj of a graded ring, and in this set we have defined a topology, and again we called it the Zariski topology. So Zariski topology on proj of a graded ring, and the properties of this some properties of this topology, and the relation between this proj of a graded ring and the n-dimensional projective space, that is also we have seen, like so if S equals to, if you take this n graded ring, so we have seen that, okay, uh, so let's start with 0 x0. So then we have n plus 1 variables. So in this case, the proj of S, and if we take the n-dimensional affine space over K, and if you go modulo by a relation, an equivalence relation, then these two sets are in one correspondence. So this is how this equivalence relation was defined, that two vectors a0 up to n and b0 up to bn are related if and only if there exists some lambda, uh, a scalar, a non-zero scalar, such that the one vector is a scalar multiple of the other vector. So in this way, we have defined this equivalence relation, and if we go modulo by this equivalence relation, we will get the proj. So this is the n-dimensional projective space over K. So how that is how these things are related. And after that, if we have a homogeneous ideal, for a homogeneous ideal, let's say I, so then we have the subset set V of I, which is subset of proj of S. So we have defined the degree of this V of I. So how we have defined this, as it is the multiplicity of so it is the multiplicity of S mod I, because I is a homogeneous ideal. So S mod I is also a graded ring. So we can talk about the Hilbert series, Hilbert polynomial, all those things. And if we take the Hilbert polynomial, we have a certain special expression for that polynomial, and that special coefficient we call it multiplicity, and that is the degree of V of I. And after that, we defined some new terminologies, uh, like for a non-homogeneous ideal or non-homogeneous polynomial, how to get a homogeneous polynomial. So this is homogenization, and also the reverse methodology, dehomogenization. And we have also studied some properties of this thing, and also homogenization of an ideal we have also seen. So homogenization, so it is not just the so if you have an ideal, let's say I, which is generated by f1 up to fn, so then homogenization of I is not just the homogenization of the polynomials, right? So we have to saturate it with respect to the maximal ideal. So those things are there. So this is homogenization of ideal. And after that, uh, we have seen if you have an ideal I, so for a homogeneous ideal I, so for a homogeneous ideal I, so we have an ideal uh, I, and here we have initial ideal of I with respect to some monomial order. So with respect to some monomial order, then we have compared the Hilbert series and other things like dimension, multiplicity, and height of these two ideals. So comparison of let's say Hilbert series, um, multiplicity, and the Krull dimension of S mod I, and dimension of S mod initial ideal of I, and also the height of I and height of the initial ideal of I. So we have compared these things. So this is for a homogeneous ideal, not for arbitrary ideal, because to define Hilbert series, we need an homogeneous ideal. And after this thing, we have defined CGG of some elements, of some homogeneous elements. And then some basic or very basic definitions from homological algebra, which we need to uh, move to the new next week. So some basic definitions from homological algebra. So in this uh, thing, we have basically seen how to define complex or chain complex. That is one thing. Then we have seen what is homology of a chain complex. And using this, we have seen when a chain complex is exact or an exact sequence. Then the pre-resolution and how to construct pre-resolution and all those things. Then minimal pre-resolution and existence of minimal pre-resolution and the graded version of those things. So mainly, then after that we have focused mainly on the graded counterparts. So I will specify it separately. Minimal graded free resolution, minimal graded free resolution, of a graded module. So of a graded module, then the uh, important theorem, Hilbert-Szigi theorem, which talks about the length of the minimal graded free resolution of a finitely generated graded module over a graded ring. So the Hilbert-Szigi theorem. And after that, we have defined the graded Betti numbers. So graded Betti numbers. And finally, the the Betti table of a graded module. And we have also seen how to compute these things in we call it 2. So these are the uh, rough summary of the topics of week 11. Okay, so now let's solve some problems. Okay, so let me write down the first problem. So let R be the polynomial ring in three variables. Here K is a field. So and this is equipped to the standard grading. That means this degree of X, degree of Y, and degree of Z. This is 1. And let I be the ideal defined by the it is generated by xy and xz. Okay, then this is also a homogeneous ideal because this is generated by homogeneous elements. So this is a graded ring and we have a homogeneous ideals. Then find the dimension of proj of r mod I. Right. So proj of r mod I is basically uh, so proj of r mod I. This is basically subset of spec of r mod I, and we know the definition of dimension of closed subsets. So we need to find the dimension of proj of r mod I. So how to do this one? Okay, uh, so first let me recall how the proj of a graded ring is defined. So recall the first thing is proj of a graded ring. So if S I will write it here. So if S equals to, let's say, K x0 up to xn, and let's say M be the homogeneous maximal ideal generated by the elements x0 up to xn, then the proj of this graded ring S is defined as the uh, P belongs to spec of S such that P is homogeneous and P is properly contained in M. So this is the set of all homogeneous prime ideal which are properly contained in the homogeneous maximal ideal, right? So this is the proj of the graded ring S. Now, in place of S, we need to have R mod I. So what is proj of R mod I, right? So first of all, R mod I should be a graded ring, and it is a graded ring because I is a homogeneous ideal. So we are going modular homogeneous ideal means we will get a graded ring. So what is proj of R mod I? So this set is basically set of all those prime ideal in spec of R mod I such that P is homogeneous and P is a proper subset of the image of the maximal ideal, and which is basically M mod I. So it is better to write M mod I in place of M bar, right? So this is proj of R mod I, and this is clearly subset of spec of R mod I, or this prime spectrum of R mod I. So we need to find the dimension of this closed subset. So one more thing. Uh, so what is dimension of a proj? So so dimension of proj of S, and if we take the dimension of S, so there is one relation. So it is basically divided by 1. So one easy way to see this is that while we are defining proj of S, we are omitting one prime ideal, which is the maximal ideal, right? So this extra prime ideal will increase the height, will decrease the height, sorry, decrease the dimension by 1. So that is why we have this relation. So you may try to write down a rigorous proof for this, but uh, now just let's use this formula to find the dimension of proj of S. So we need to find the dimension of proj of R mod I. So if we find dimension of R mod I, then we are done. So thus, to find dimension of proj of R mod I, we need to find dimension of R mod I, right? So this is the final task for this problem. So we have to find dimension of this quotient ring, and this is what we have already done in the earlier live problem solving sessions. So we have so many ways to do this, and we can also use the Macaulay tool. But since the ideal is very simple, so let's do it by hand. So what is R mod I? Now R mod I is basically the polynomial ring in three variables modulo by the ideal generated by xy and xz. So we need to find dimension of this. So also recall one more thing. Uh, Recall that so dimension of R is basically uh, supremum of dimension of, okay, not R, let's denote it by S because we have fixed R. So dimension of S modulo P such that P is a minimal prime of S, right? So this is something we have already seen, or if you have not seen, you may try to prove this. This is a very simple formula. So we will use this one. So we need to find the minimal primes of this. So that is basically the minimal primes of this ideal. So there are several ways to find the minimal primes. First we will find the minimal primes. Hence, uh, first we will find the minimal primes of the ideal I, which is generated by xy comma xz, right? So we need to find the minimal primes of this ideal. So we can directly find the minimal primes, or we can use the primary decomposition, or we can use the Macaulay tool. So let's find it by using the primary decomposition. So now our I is basically xy comma xz. So we need to decompose this. So this is basically xy comma x intersection xy comma z. Because GCD of x and z is 1, so we can decompose it like this. But here xy is already in the ideal generated by x. So this is ideal generated by x intersection xy comma z. Now here GCD of xy is 1. So again we can decompose this part. So let's do it. So it is ideal generated by x intersection with ideal generated by x comma z intersection with ideal generated by y comma z. Now we need to cancel out the irredundant parts. So ideal generated by x comma z. So multiples of x are already here and multiples of z are already in here. So this part is irredundant. So this is basically ideal generated by x intersection with ideal generated by y comma z. So our ideal I is basically intersection of these two prime ideals. So we can write associate primes of I, which is just basically associate primes of R mod I is ideal generated by x, comma ideal generated by y, comma z. But these two primes are minimal primes because these are incomparable. So this is same as minimal primes of R mod I. So now we can find the dimension of R mod I. So thus dimension of R mod I is supremum of dimension of R mod ideal generated by X, comma dimension of R mod ideal generated by Y, comma Z. But what is these two rings, R mod X and R mod Y, comma Z? So this is basically dimension of K, Y, comma Z, and the second one is dimension of Kx, right? So this is because Kxyz modulo ideal generated by X is basically isomorphic with Ky, comma Z. So this is very well known. And similarly, the second one, Kxyz modulo ideal generated by Y, comma Z is isomorphic with Kx. So this is polynomial ring in two variables. This is polynomial ring in one variable. And we already know how to compute dimension of polynomial rings. So this is basically supremum of, so this is Kyz. We have two variables. So dimension is 2. And the dimension of this part is 1. So this dimension is basically 2. So we have got dimension of R mod I. So now we can use this formula. Thus, dimension of proj of R mod I is dimension of R mod I minus 1, which is basically 1. So this is the final answer. So this problem is very simple. Okay, so now let's do the next one. So okay, let me write down the second problem. So let R be the polynomial ring in two variables x, y over the field of complex numbers. And here also degree of x and degree of y is 1. So this is, we are taking graded part. We are taking the standard grading of this polynomial ring. And let I be the ideal defined by x minus y. So this is a homogeneous ideal in R. Okay, so this is a true false type question. I forgot to mention. So this is true or false. So R is this polynomial ring with standard gradation, and I be this homogeneous ideal generated by x minus y. Then this proj of R mod I intersects the open set u of y, which is basically subset of the one-dimensional projective space over C. one-dimensional complex projective space. So we are given this polynomial ring with standard gradation. We are given this homogeneous idea. Then we can have this proj of R mod I, because R mod I is a graded ring, and this is equipped with the Zariski topology, and this is in 1-1 correspondence with P1 of C. Oh, sorry, this is R mod I, so not with P1 of C, but a subset of P1 of C. So we need to check that this proj will intersect with this open set U of Y or not. Okay, so let's see how to solve this. So let's recall the basic definitions which we need to solve this problem. So first of all, we have already seen what do we mean by proj of R mod I. So let's see. Okay, let me write down it one more time. So what is proj of R mod I? So this is the P belongs to spec of R mod I such that P is homogeneous and P is proper subset of, uh, in this case, it is proper subset of the homogeneous maximal ideal, which is x bar comma y bar, generated by x bar comma y bar. Now here what is V of I? So this is the graded counterpart of what we have learned already. So this is P belongs to proj of R such that P contains I. So this is basically proj of R mod I, right? And now using this d of I, we will define what we mean by u of y. So what is u of y? This is basically the complement of, so first you take the proj and you take the complement of d of I in proj of R. This is defined as u of y. So if we write this set explicitly, then this is basically set of all those homogeneous prime ideal in proj of R such that uh, I is subset of P and Y does not belongs to P. Or we can write it as all those homogeneous prime ideal in proj of R mod I such that Y does not belongs to P. So recall that these are basically the uh, yes. So these are basic open sets for the Zariski topology on proj of R mod I. So basic open sets for the Zariski topology on proj of R mod I. So we need to check proj of I think uh, this is not correct. So let's forget this and this part also. So this is just all those prime ideals such that y does not belongs to p. So we need to check. We need to check uh, proj of r mod I intersection uy is empty or not. So that is the question. Oh, so this is v of y. This is my bad. Yes, this is complement of this thing. So this is v of y. So this is now the definition makes sense. So we need to check about this intersection. So what happens if this intersection is empty? So suppose this proj of r mod I intersection this open set uy is empty. Now what does this means? So this implies for every p belongs to proj of r, uh, p contains I. That means p is in proj of r mod I if and only if p is not in u of y. If and only if y does not belongs to p, because this intersection is empty. Sorry, p belongs to p, y belongs to p, because p does not belongs to u of y, so y has to belongs to p. And this implies, which implies y belongs to p for all p belongs to proj of r and p contains I. So this will imply y belongs to the radical of I. Now what is radical of I? Now our I is just x minus y. So this is a prime ideal. This is a prime ideal. Why this is a prime ideal? Because if you go modulo this ideal, so this can be identified with this ring, polynomial ring in one variable, and is a domain. So this ideal has to be prime ideal. So since it is a prime ideal, so it has to be a radical. So I is a radical ideal. So that this implies I is equals to radical of I. But this y does not belongs to ideal generated by x minus y. But y does not belongs to ideal generated by x minus y. So this is very easy to check uh, because both are prime elements, so they cannot divide each other, right? So this is a contradiction. So this is a contradiction. But contradiction to what? So we have assumed that this intersection is intersection is empty. So this is a contradiction. So hence, uh, this proj of R mod I intersection U of Y must be non-empty. So this is in fact true. So proj of R mod I must intersect this open set U of Y. So yeah, okay. So let's move on to the next problem, which is problem number 3. Okay, so let X be a projective variety. Let X be a projective variety in three-dimensional projective space over some field K, and suppose the Hilbert polynomial so X be a projective variety in P3K, and the Hilbert polynomial of X is basically P2 plus 3 P3. Then choose the most correct statement from the following statements. Choose the most correct statement from the following statements. From the following statements. So the first one is X is irreducible, and second one is X is union of two lines. X is union of two straight lines. And the third is X is defined by a quadratic homogeneous polynomial. Sorry, yes, quadratic homogeneous polynomial. Okay. Oh, okay. This should be 2. Okay, so let's see what this question is saying. So let X be a projective variety in P3, and the Hilbert polynomial of X is given, which is P2 plus 2P3. This is the notation which used in Macaulay 2. Then what is the most correct statement among these three statements? Is X a irreducible topological space, or X is union of two lines, or X is defined by a second degree homogeneous polynomial? So let's try to solve this. So what is projective variety? So recall uh, X is a projective variety in P3, P3K. So what does it means? So that means X equals to some V of I, and what is I? Where I subset of, since it is P3K, so we need to choose four variables. So x0 up to x3. So I subset of this polynomial ring, where I subset of this a homogeneous ideal, and V of I is basically the subset of proj of this ring k x0 up to x3, and that is uh, so proj of k x0 up to x3 is in 1-1 correspondence with P3K. So, and here we have the set X. So here we have the set V of I. So this is the algebra part. This is the geometric part. And what is Hilbert polynomial of X? So Hilbert polynomial of X means Hilbert polynomial of this quotient ring R mod I. So this is the terminology we are using. So we are given the description of this Hilbert polynomial of R mod I. Using this, we need to give description of this projective variety X. So how to do this? So what information we can get, and also I should recall what is. So Hilbert polynomial of X is P2 plus 2P3, right? That is what is given. But what is P2 and P3? So where recall that Pi is basically, okay, so if we denote it by Pi of T, so it is basically T choose I, sorry, T plus I choose I. So this is the polynomial Pi, P of I. Okay, so this is the given information. Now from this, what we can conclude? So now uh, here the highest term is 3. So dimension of X is 3. Since in so I forgot the notation for Hilbert polynomial, so let's denote it by hi of t. So which should be looked like sorry, it is e of I, Hilbert coefficient of R mod I, and t plus, sorry, it should be p of I. So it should be 0. So I greater equals to 0. And the largest I for this pi is non-zero will give the dimension of x or dimension of R mod I. Okay, so okay, I should write it here. It's so dimension of x is basically the dimension of the coordinate ring, which is k x0 to x3 modulo I, and this is 3 because p3 is non-zero. So we have got dimension of k0 up to x3 mod I. So this will imply, uh, so recall the formula that uh, height of I plus dimension of this quotient modulo I is same as dimension of kx0 up to x3. So this is something we have already seen. So from this we can write height of I. So this is polynomial ring in 4 variables. So dimension is 4. 4 minus dimension of this quotient ring is 3. So this is simply 1. So thus I is a homogeneous ideal of height 1 in the polynomial ring k x0 up to x3, right? But this polynomial ring is a UFD, and in a UFD, so I also write this. So in a UFD, every and am I missing something? Should be. So in a UFD, every height 1 prime ideal is principal. So we have, I think we have done this problem in the lectures. So thus, hence, I should be generated by f, where f is a homogeneous polynomial in k x0 up to x3, right? Also, the Hilbert polynomial is p2 plus 2p3. So this multiplicity is 2. Also, since Hilbert polynomial of R mod I is p2 plus 2p3, so the multiplicity of I is 2. Thus, F is a quadratic or degree 2 homogeneous polynomial. So, and x, which is defined by v of I, which is v of a. So, x is defined by a quadratic homogeneous polynomial. So, the option C is correct. So, option C. Okay. So, let's solve the next one. So, this is problem. This was problem number 3. So, next is problem number 4. So, again, let R is the polynomial ring in 3 variables. Let's say x, y, z, and let's take the monomial order G-lex with G-lex order. And also we need to uh, define the order on the variables x, y, z. So let's x greater than y greater than z. Then if you take the S polynomial of the polynomials xy and xz, then this S polynomial gives a CGG which is z times xy minus y times xz equals to 0. So this is true or false. So this problem is very simple. So take the polynomial ring in 3 variables with G-lex order, where the variables are ordered in this way: x greater than y greater than z. Now take these two polynomial xy and xz. Take the S polynomial of this, and does this gives a CGG like this? Okay, to solve this problem, I should recall the definition of S polynomial and CGG first. So let's do this. So recall that definition of S polynomial. So let Fg belongs to R k x1 up to xn with the monomial order less than, then the S polynomial of f and g, the S polynomial of f and g is defined as, so it is basically denoted by s of f comma g. So this is the notation. And how it is defined? So it is basically the, so you take the, so we are in the polynomial ring which is UFD. So we can talk about LCM and GCD. So let's take LCM of the initial term of f and the initial term of g, divide it by the uh, coefficient of the initial term of f times the initial term of f, multiply it with f. Okay, I need some more space. So yeah, and subtract it. So again, take the same numerator, LCM of initial term of f and initial term of g. Okay, I also need some more space. Yeah, divide it by the coefficient of the leading term or initial term of g and multiply it with g. So here basically we are cancelling out the leading terms, right? So that this is the definition of S polynomial of f comma g, f and g. So uh, so this is the definition of S polynomial. And second one, what is CGD? So for polynomials, let's say f1 up to fm belongs to, let's say, kx1 up to xn, a CGD of f1 up to fm is an expression of the form summation ri times fi is equals to 0, where I is running from 1 to n, where this ri belongs to kx1 up to xn. So an equation of this form is called a CGD of these elements f1 up to fm. So these are the two definitions we need to solve this problem. We also need Gmax order, but we don't need that much, but it's okay. So first of all, let's compute this S polynomial. Then we will compute CGGs of these two element. Then we will see we are getting this same relation or not. So that is the task. So now, so what is S? So what is S polynomial of xy comma xz? So this is by definition LCM of initial degree of, sorry, initial term of xy comma initial term of xz, and the coefficient is 1, initial term of xy times xy, and subtract the same numerator, initial term of xy with initial term of xz, divided by the coefficient 1 times initial term of xz times xz. So this is the thing we have to compute. So initial term of xy is xy itself, because we have only one monomial, so we don't have to compare it with anything else. So it is LCM of xy comma xz, because initial term of xz is xz itself, divided by again xy times xy minus the same thing LCM of xy comma xz divided by xz comma xz. So now this xy will cancel out. Similarly, this xz will cancel out. Now what is LCM of xy and xz? So this is also very simple. It is just xyz minus xyz, and this is 0. And this is the same thing, right? Uh, so this is z times xy means xyz, y times xz means xyz. So this we are getting. Now we need to compute CGE of. So now let's compute CGE of xy comma xz. So we need to find uh, relations or expressions of this form. So how to do this one? So let I be the ideal generated by uh, xy comma xz, and define the map I from R2 to I. So okay, I have not defined R. Okay, R is this polynomial in three variables I have defined. So define this by sending E1 to xy and this basis element E2 to xz. So E1 basically 1 comma 0, E2 basically 0 comma 1. So this is an R linear map. So then phi is a R linear map. What is kernel of phi? So kernel of phi is basically R1 E1 plus R2 E2 belongs to R2, such that phi of R1 E1 plus R2 E2 is 0. But what is this? This is R1 E1 plus R2 E2 belongs to R2, such that uh, R1 XY plus R2 XZ is 0. So this is basically collection of all R1 R2 which gives CGG of this XY and XZ. So basically, to find the CGG of XY and XZ, we need to find this kernel, right? So how to find this kernel? So R1 X1, so R1 XY plus R2 XZ equals to 0. So here x is common and we are in an integral domain, so we can cancel out x. So this is R1y plus R2z equals to 0. This implies R1y is equals to minus R2z. This will imply y divides minus R2 and z divides R1. So R1 is equals to some s times z for some s belongs to R. Now let's put this into this equation. So szy plus R2z equals to 0. So we can again cancel out z. So R2 is basically minus sy. So R1 U1 plus R2 E2 is basically some S times uh, Z E1 minus Y E2, right? So this is the uh, and what is phi of Z E1 minus Y E2 is Z times XY minus so this element is in the kernel, so image is 0. So that will imply y times xz is 0. So this is a CGD. So the above relation is a CGD of xy and xz, and which is basically given by the S polynomial, right? This. So this result is so this problem is true. So we have to find this S polynomial and we need to find the CGD. So that is what we have to do here. So this completes this problem. It is problem number 4. Okay, let's move on. Okay, let's do the next problem. So this is problem number 6. So let R equals to kxy be the graded ring where degree of x and degree of y is 1, and uh, and I be the ideal generated by the homogeneous elements x square comma xy comma y cube. So I is a homogeneous ideal. Then we have two problems. So write down the Betty table of R mod I, and second one, find the graded Betty number 2 comma 3 of R mod I. 2 comma 3th Betty number of R mod I. So this is the problem. So first let's recall what is Betty table. So what is Betty table? So I will write down in the more general form. So if R is a n graded ring with zeroth component R naught is a field. Okay, we need Noetherianness. So so let R be a Noetherian n-graded ring with zeroth component is a field, and M be a finitely generated Z-graded R module, right? Then, since M is finitely generated and it is Z-graded, then we can have a minimal graded free resolution of M. Then we can write the minimal graded free resolution of M as, so you take M first and subject it a graded free module. If not, let's call this map as epsilon. Again take F1, a graded free module, let's take delta 1. Again take graded free module F2, let's say is delta 2, and so on. Where this Fi can be written as direct sum of R shifted by minus j power beta I comma j of M, and this is varying over z. And this delta I and epsilon are graded homomorphisms. So here we have the graded free modules Fi, and these homomorphisms are also graded such that this free resolution is minimal free resolution, right? Then these beta ij's are called I comma jth petty number of M. So, but what is beta ij in words? And beta I comma j of M is basically we write it as I comma jth Betti number of M. This is defined as the number of copies of R shifted by minus j in this ith module of the resolution, or this is same as the number of generators in the free module Fi which has degree j, right? So this is the I comma j Betti number of M. Now using these numbers, one creates a table which is known as Betti table of M. This is basically, so if you take 0, 1, 2, again you take 0, 1, 2, so here you have the number of rows and here the number of columns. The first entry is beta 0 comma 0 of M. Second entry is beta 0 comma 1 of M. This entry is beta 0 comma 2 of M. This entry is beta of 1 comma 1 of m. This entry beta of 1 comma 2 of m, and this is so on. We can take up to as much we have. So this is beta 1 comma 3 of m. This is beta 2 comma 2 of m, beta 2 comma 3 of m, and so on. So here I comma jth entry in the table is beta of I comma I plus j of m, not beta ij of m. Okay, so that is one needs to take care. So to write down this Betty table, we need to find this all these graded Betty numbers of n. And to find these graded Betty numbers, we need to find this minimal graded resolution of n. So we have to do it for R mod I here. Okay, so let's do this. So let's write. So one can do this in Macaulay very easily, but in this case, we will do it by hand. Let's write down the minimal graded pre-resolution of R mod I. So we will take R mod I first and subject it from a pre-module. So we can take R itself and take the canonical map, which is graded also. But what is the kernel of this map? So kernel of this map, so which will take just pi here, not epsilon, because it's the canonical surjection. Kernel of this map is I, which is x square xy y cube, and we have this injection. So we need some pre-module here, and we some pre-module, and we need to subject it here. So we have three generators. So let's take R3. So let phi from R3 to I defined by E1 maps to x square, E2 maps to xy, E3 maps to y cube. Then phi is R linear. Then phi is surjective. So phi is onto R linear map. So and so we need graded pre-resolution, right? So we need the homomorphisms also graded. But to make this map graded, uh, here E1 is basically 1 comma 0. So which is degree 0. But here right hand side we have degree 2. So we need to shift the degrees, make this homomorphism a graded homomorphism. And to make phi graded, we shift the degrees as follows. So we take phi from so first one is goes to x square, which is degree 2. Xy is of degree 2, but yq is of degree 3. So first one is of degree 2, so r minus 2. Second one is also degree 2, so r minus 2. Third one is of degree 3, so r minus 3, and map it to I. So here we have some free module. It is F1, and we will take surjection, and we will take this composition. So this is phi 1 and this will be delta 1. So let delta 1 is phi compose I. I1 is this inclusion. So we have r mod I to 0 to r, and if here we have r minus 2, direct sum r minus 2, direct sum r minus 3 to here, which is delta 1. Now again we need to find the kernel of this delta 1 to construct the free resolution. So here we will have this kernel of delta 1 and we have this injection I2. We have this free module, we need to subject this. Then we can construct this free resolution by taking the composition. So first we need to find this kernel of delta 1. So we need to find the kernel of delta 1. So again it is just the CG of these three elements. So we need to find those relations. So one can do it by hand, but that is laborious. So one can use the Macaulay tool also. So I am just writing it down and you can check it via Macaulay tool. Uh, okay. So kernel of delta 1 is basically the submodule generated by R1 times y minus x 0, this vector, plus R2 0 y square minus x, such that this R1 R2 belongs to R. So the resolution becomes R to R mod I as usual the pi, then R minus 2, R minus again 2, R minus 3, this is the delta 1, and here it is a two vectors and three entries, so it will be 3 cross 2. So we have R2 here and degrees are shifting by 1 here, so we have R minus 3 and R minus 4. So R minus 3, direct sum R minus 4, this is delta 2, and one can check that this map will be injective. So this is zeroth component free module, this is the zeroth component, this is the first component, this is the second component, this is F2, this is F1, this is F0. So now we can write down the Betty numbers. So so let's write down the Betty table itself. So 0 1 2, 0 1 2. So here we have beta 0 comma 0, beta 0 comma 1, beta 0 comma 2. Here beta 1 comma 1, beta 1 comma 2, beta 2 comma 2, and so on. So beta 0 comma 0 means in the 0th free module, copies shifted by minus 0. So number of copies of R minus 0 in F0. So this is 1. Now beta 0 comma 1. So in f0 number of copies of r minus 1, so we have only one copy, so it is just other will be 0. Now this one, which is beta 1 comma 1, that means number of copies of r minus 1 in f1. So we have only r minus 2 and r minus 3, so it will be 0. But beta 1 comma 2, which is number of copies of r minus 2 in f1. So we have 2 here, so it will be 2. So it is 0 and it is 2. Similarly, one can check number of copies of r minus 3 is 1, so it is 1. Similarly, it will be 0, 1 and 1. So this will be the only Betti table. So this is the Betti table of R mod I. Now, so this completes the first part. Yeah, and we need to find beta of 2 comma 3. So beta of 2 comma 3 means this is the second beta 2 comma 2, this is beta 2 comma 3. From the table we can see beta 2 comma 3 of r mod I is 1. So if you want to do this by hand, one needs to be very careful also in computing these shiftings, but one can do this very easily in Macaulay too. So this completes this problem. Okay, so I think it's a good time to stop. Mm, okay, so we will again meet in the next week.